Welcome friend, in the next lecture of Calculus First. In the previous lecture we discussed monotone sequence and some example of monotonic sequence. Also we proved monotone convergence theorem. So what is the statement of this? A monotone sequence of a real number is convergent if and only if it is bounded. So we proved already this theorem. Now in this lecture we have to solve some example using this monotone convergence theorem. So our today's topic, that is application of monotone convergence theorem. Application of monotone convergence theorem. What it means, we have to solve some examples on the monotone convergence theorem. So first example, so our first problem is establish the convergence or divergence of the sequence xn where xn is equal to 1 upon n plus 1 plus 1 upon n plus 2 plus dot dot plus 1 upon 2n for all n belongs to the natural number. So write down first given what is our xn? Xn is equal to 1 upon n plus 1 plus 1 upon n plus 2 and dot 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 1 upon 2n. Again for all n belongs to the natural number. So can you write xn plus 1? Just replace this n by n plus 1. So what we are getting? 1 upon n plus 1 plus 1 plus 1 upon n plus 1 plus 2, and like this you can write 1 upon n plus 1 into plus what? 3 and dot dot. You can write this is 1 upon 2 n plus 1. This is again holds for all n belongs to the natural number. What is this? Just do simplify n plus 2 plus 1 upon n plus 3 and dot dot. You can write this is our 1 upon 2n plus 2. This is 2n plus 2. And before this sum you can write some terms, that is 1 upon 2n plus 1. Then you can write here again 1 upon 2n. Okay, you can write like this. Is it? That is 2n plus 1, 2n plus 2. Say this is equation number 1 and this is equation number 2. So from first and second, xn plus 1 minus xn, it is equal to. So do subtraction of this term, these two sequences. So are these two terms xn and xn plus 1. Then what you are getting? This n plus 1 is remain same. This is first n plus 2 get cancelled, n plus 3 get cancelled, 2n get cancelled. That means after this is we are getting cancelled, or we write this all these things, n plus 2 plus 1 upon n plus 2 or 3 and dot dot 1 upon 2n plus 1 upon 2n plus 1 plus 1 upon 2n plus 2 minus what? We have xn. So just to subtract n plus 1 minus 1 upon n plus 2 and so on, minus 1 upon n plus 3, and you can write like this, minus 1 upon 2n. Is it? This. So now if you see this, all these terms are get cancelled. Similarly after this all the terms are get cancelled. So what is remaining here? 1 upon 2n plus 1 plus 1 upon 2n plus 2 minus 1 upon this one term is remains, that is n plus 1. If you take here 2 common, then what is remaining here? 1 upon 2n plus 1, 2n plus 1 plus 1 upon 2 is common, then it is n plus 1 minus 1 upon n plus 1. These two terms are like terms, so you can do subtraction. Half minus 1, it should be what? It should be minus half, that is 2n plus 1. Just do subtraction. Now you have to do the simplification. Then what you are getting? 2n plus 1 minus 2n plus 1 upon 2n plus 1 into 2n plus 1. So do simplification. What you are getting? 2n plus 2 minus 2n minus 1 upon 2 into n plus 1, 2n plus 1. Now if you see here, this will get cancelled, and what is remaining? 1 upon this 2 minus 1 is 1, 2 into n plus 1, 2n plus 1. Now if you see this n is positive, therefore it should be greater than 0. It should be greater than 0, and therefore you can write this xn plus 1 minus xn is greater than 0, and that is you can write xn plus 1 is greater than xn, that is you can write xn is less than xn plus 1 for all n belongs to the natural number, for all n belongs to the natural number, and therefore we can say that therefore x is equal to xn is a which sequence, increasing or decreasing? It is a increasing sequence. Increasing sequence. Now what we have to do? We have to use the monotone convergence theorem. The sequence is increasing, therefore it is monotone. Hence monotone. Hence monotone. So hence it is monotone sequence. And now what we have to prove? We have to prove this sequence is convergence or divergence. And for this, what is our theorem? If the monotone sequence of a real number is convergent if and only if it is bounded. We have to show convergent, therefore we have to show it is a bounded sequence. First we show it is monotone, now we show it is a bounded sequence. How we prove this? How we prove this? We have xn is equal to 1 upon n plus 1 plus 1 upon n plus 2 plus and so on. We can write it is 1 upon 2n. And we can write this is strictly less than or equal to, we can say that it is less than or equal to 1 upon n plus 1 upon n plus and so on 1 upon is equal to n upon n, it is equal to what? 1. And hence we can write 0 is less than xn is strictly less than what? 1. It is strictly less than 1. Here we can write it is a strictly less than. Hence what we can say? Thus xn is bounded monotone sequence. Hence xn is convergent by monotone convergence theorem. By monotone convergence theorem. Okay, so this is a very simple example and important example for the examination. So you have to establish the convergence or divergence. So try to show that it is increasing or decreasing sequence, and then you have to use the monotone convergence theorem. Is it? Okay, so it is bounded, hence bounded, then we show that it is monotone, increasing and bounded sequence, hence therefore it is convergent, and this converges to what? Which limit? it is increasing, hence it is supremum. It converges to the supremum. But just we have to establish the convergence, so we are not going to find the limit of this sequence. Similarly, we solve the second example. Okay, so we solve one more example. That is, establish the convergence and find the limit of the sequence 1 plus 1 upon n raised to n plus 1. So what we assume, let xn is equal to 1 plus 1 upon n raised to n plus 1. So we assume this is our xn. Now what we have to find, if the limit exists then it is convergence, if the limit is not exist then it is divergent. So try to prove limit n tends to infinity of xn, it is equal to what? Limit n tends to infinity 1 plus 1 upon n raised to n plus 1, and it should be equal to n. If n tends to infinity, you can write 1 plus 1 upon n into limit n tends to infinity 1 plus 1 upon n raised to what? N. Just we split the index. And it is equal to what? This limit n tends to infinity, this is 1 plus 0, and this limit of this is our e. This limit is e. Just write down the here formula. Limit n tends to infinity 1 plus 1 upon n raised to n is equal to e. It is equal to e, and it is equal to e. Therefore limit n tends to infinity xn is equal to what? E. Therefore what we can say, that the sequence xn is convergence and it is convergence to E. Therefore it is convergence to example. No need to use the monotone convergence theorem. Okay. In the similar way, we will solve the one more example. Now we prove next example. Let x1 is given, x1 is equal to 8 and xn plus 1 is equal to 1 upon 2 xn plus 2. For all n belongs to the natural number. Show that xn is bounded and monotone. Find the limit. So what is given? Given x1 is equal to 8, and what is given one more? Xn plus 1 is equal to 1 upon 2 xn plus 2. Now if you see, x1 is equal to 8, x2 you can find, x3, x4, x5 you can find, is it? And there is no chance to get a negative numbers in the sequence. Hence what we can say, that hence xn is a sequence of positive number. Hence it must be bounded below. Is it? Negative terms you are not getting here, therefore it must be bounded below. It must be bounded below by 0, 1, 2 and so on other number. Is it? Therefore x1 is 8 is given and it is this, therefore all the terms are positive and hence it must be bounded below. What we have to show? It is bounded we have to show. Then we have to show it is a monotone, and then we have to find the limit. So our claim first. What we prove? Claim first. xn is bounded sequence. First our claim is xn is a bounded sequence. It is bounded below. So for this we have to prove. What we have to prove? It is bounded below already. So we have to prove xn is bounded above. We have to prove it is xn is bounded above. So what we have given? x1 is equal to what? 8. So what is x2? What is x2? This can be write this formula for x2. It is equal to what? 1 upon 2 x1 plus 2. What should be this? What should be this? 1 upon 2 into 8 plus 2. And it is equal to what? This should be what? 4 plus 2, and it is equal to 6. It is equal to what? 6. Therefore, and if you find x3 is equal to what? x2 is what? Our 6. x2 is equal to 6. Now x3 is equal to what? You can find this a1 upon 2 into x2 plus what? 2, and therefore 1 upon 2. This 1 upon 2 into x2 is 6 plus 2. It is equal to 3 plus 2. It should be 5. That means what you can say, first number is greater, then from this what we can say, x1 is greater than, x2 is greater than what? x3 and dot dot. And this x1 is equal to what? This is our 8. That means what? All the numbers, all the xn, therefore thus we can show xn is less than or equal to 8 by induction. We can show this xn is less than or equal to 8 by using the mathematical induction. We have what? x1 is less than or equal to 8. Thus what we can say? The result is true for n is equal to 1. Now in the induction what we have to do? We have to assume now. So assume that the result is true for n is equal to k, and that is what we can say, that is xk is less than or equal to 8. xk is less than or equal to 8. Now what you have to prove in the next step? To prove the result is true for xk plus 1. That is what? xk plus 1 is less than or equal to 8. xk plus 1 is less than or equal to 8. Okay. So what we have xk plus 1. It is equal to, write down this formula, that is 1 upon 2 xk plus 2. And it is less than or equal to what? This is 1 upon 2 into what is the value of xk? Maximum value 8 plus 2. What we can say here? How much? This should be what? This should be, this is equal to 4 plus 2 is equal to 6, which is less than or equal to, and it is strictly less than 8. And therefore what we can say, xn plus 1 is less than or equal to 8. xk plus 1 is less than or equal to 8. Hence by mathematical induction, we can say the result is true for x all n belongs to the n, that is natural number. That is what we can say, xn plus 1 or xn is less than or equal to 8 for all n belongs to the natural number. And therefore what we can say, therefore the sequence xn is bounded above. And this sequence is bounded above, and therefore we can say xn is bounded above. Hence we can say the sequence xn is bounded below and bounded above. Hence it is therefore what we can say that Xn is bounded. Similarly what we can show? Similarly we can prove the sequence Xn is bounded below by 4. Bounded below by 4, we can show this. Now we have to show, or we have to prove claim second. Now it is proved claim first. Now we have to prove the claim second. First is what? Bounded we prove. Now what we have to do? We have to prove a monotone. Now what we have to prove? It is this sequence is a monotone. Monotone means what? Increasing or decreasing sequence. So what we do? Now we prove, Xn is monotone sequence. Monotone sequence. How we have to prove this? We have to consider Xn minus 1 or Xn plus 1 minus Xn. Xn plus 1 minus Xn. Try to solve this. You will get the answer. Okay. So what we have to consider? We have to consider what we have to consider here? Xn plus 1 minus Xn. It is equal to 1 upon 2 Xn plus 2 minus what? Xn, and it is equal to do calculation 2 minus 1 upon 2 Xn, and if you write this is less than what? 2 minus 1 upon 2 into 4. 2 minus 2 into, this is what? Bounded below by 4, therefore we are written this. Okay, and this should be what? This should be, we are writing it is 2, therefore it is equal to 0. Therefore Xn plus 1 minus Xn is less than 0 or less than or equal to 0. Therefore Xn plus 1 is less than Xn, and this implies that what we can say that the sequence Xn is, this is for all n belongs to the natural number, sequence Xn is bound. It is increasing or decreasing? This sequence is decreasing. Sequence is decreasing, hence monotone. Hence it is monotone decreasing. Therefore what we proved, this sequence is monotone, this sequence is bounded, therefore by the monotone convergence theorem, what we can write? Theorem, the sequence Xn is what? Convergent. It is convergence. So it is convergent, then what we can say that now, and therefore we assume let limit n tends to infinity Xn is equal to n. That is the sequence, or we can write suppose Xn converges to what we can write? X. Suppose Xn converges to the X, and therefore we have to take here X. Okay. Then what we can write? This implies limit n tends to infinity Xn plus 1, it is equal to limit n tends to infinity Xn. We know the limit of the sequences both are equal, and therefore what we can write? Therefore just put the value of Xn plus 1 and put the limit, you will get the value of X. So what should be this? limit n tends to infinity. This is 1 upon 2xn plus 2. It is equal to limit n tends to infinity xn. So what should be, if you give it limit both the term, then it is 1 upon 2 into xn limit is x plus 2. It is equal to x. And if you try to solve this, 2 is equal to x minus half x, and therefore it is nothing but 1 upon 2 x, and therefore what we can say, x is equal to 1 upon 2x is equal to 2. Therefore what we can write, x is equal to 4. Therefore the given sequence is converges to 4. Okay, in a similar way we will solve so many problems. We will solve some extra problem in the practical session. So today we will stop here. Thank you.